Please give a big round of applause to Professor Anton van den Hengel.
Thank you very much. It's clear that I need to get better at writing a shorter bio as well, right? Yeah, wonderful to be here. Thanks for inviting me. This is my first time in Vietnam. It's fantastic. Half the title of my talk seems to have disappeared off the side there, which is going to be interesting because that means that something's changed the fonts on my slides, so I'm going to wind up pointing a lot. It's very good of the last three speakers to do the intro to my talk for me. I'm actually on my way out of Amazon, right? And so I was, until very recently, a director of machine learning there. And going into Amazon, I was a bit of a skeptic about continual learning, right? I guess I saw it as just a flavor, right? Or an additional level of difficulty or something. But having worked on those practical problems for 4 years, I can tell you that it's absolutely critical. And part of what I want to convince you is that more of us should be thinking about our problems as continual learning problems instead of this artificial thing that we do, whereby we kind of run a version of machine learning whereby we just assume that the data is available, that it's always going to be the same, that there's no drift, that that everything's a kind of perfect, false, mythical, wonderful world where data reigns upon you in its perfect form, and you don't have to fight with distribution drift or the real world or any of this sort of stuff. All right, so yeah, that may not be the optimal way to present these slides, right? I'm not sure whether it's better that you can read half of them or that we go with the automatic advance thing that you had for going for Angela. I'm happy either way, right? Actually, I'm happy to do it with just a black screen. I'll just wave my hands if you like. Anyway, there's even it's about 4 slides missing in that. Anyway, the message is relatively, it doesn't really need the pictures. To tell you the truth, most of the pictures are an example of me eating my own dog food, right? All right, fantastic. How about that? All right. Still. All right. Okay. So these, as you can tell, images generated by generative models, and no real images were harmed in the creation of this talk, right? They're all completely synthetic, and we do live in a time where there's a whole lot of change going on, right? And I think that a lot of the mythology that we have in machine learning hasn't caught up, right? So we assume in continual learning particularly that we've got nothing to start with, right? So continual learning is this idea that the model's got to develop as you progress, right? That in the real world, when you're developing machine learning algorithms, right, they've got to actually do something productive that aren't just written for CVPR papers, right? You're not just hoping for bold numbers in the right places. If you want to write algorithms that work for real problems, then you've got to deal with the fact that the world is constantly changing, right? But the traditional way to do continual learning is kind of based on this assumption that all we can do is hope to get to be as good as the supervised version of the problem, right? Where you're given all the data to start with. Yeah, that we're going to be given the data slowly, right? You turn your algorithm on, it's complete cold start, right? Doesn't know anything about the world, and you just keep getting better and better and better and better. And by the time you've got to the end of your process, that you've seen all of the data, and that maybe if you're really good, you might be as good as you would have been back here if you'd seen all the data to start with, right? That's a lie, right? That's a complete fiction, because if you're starting here, then either you're learning as you go, right? You're getting better. I'm starting to feel good about this. I've got a bit going on. And by the time I get here, I'm about 3/4 of the way down. I'm starting to get functional, right? Things are actually happening. The traditional method is starting back here. I've got no data, right? I've got no data. I've got no data. I've got no data, because I'm not going to do anything until I've seen the whole thing, right? Suddenly I've got all the data and I can do something. All of that space in there, I've been completely dysfunctional. I'm not doing anything. I'm standing around twiddling my thumbs, right? So, when you're dealing with real problems, it's just not true that the best we can do is wait and then train, right? The next part of the mythology is that when you get over here, right, you've seen all your data and you train, and then you fix your model. And you just keep going, right? You're stuck with that model and you just keep going with that model forever, which is also rubbish, right? Because you're continuously getting new data as you move along, right? And the reason that this assumption is that you can't get, that all you can do is hopefully kind of asymptotically approach the supervised performance, is because you assume that you start here with no information, which is also not true, right? Because if you start here, you already know what the problem is, right? Nobody says to you, I want you to devise a machine learning application, but I'm not going to tell you what the problem is, right? It's a secret. You have to just, give me it's not just you're giving us a black box, right? It's a black problem. We're not even going to tell you what it is. Everybody's always going to tell you it's for a driverless car, right? Or you're going to recognize content of images, or you're going to, summarize documents or whatever. You know what the problem is when you get in. And pretending that you don't know what the problem is just daft, right? And there's if we know what the problem is, we can bring a whole lot of other information to solving that problem. And maybe by the time we get over here, with us doing better than the fully supervised model was over there, right? Also, it deals with the reality of these things. So continual learning is, as far as I'm concerned, it's critical. Most of the models out there use a rehearsal buffer, right? What a rehearsal buffer means is that as I'm collecting this data as I go through the process, that I'm going to keep a subset of it, right? I haven't got enough capacity to keep all of it, so I'm just going to remember the key bits of data that will allow me to not lose too much performance from all the stuff that I'm not remembering by the time I get over here, right? The trouble with and it's a good idea, yeah? A rehearsal buffer is a fantastic solution. The trouble is that it leads you to this position where you're only ever approximating the fully labeled, fully supervised, version of the problem. And you get, there's 1,000 strategies for how you select which data elements to keep and then how you use them, right? All fantastic, but the key problem with that is that you wind up with this idea of catastrophic forgetting, right? Which just really means that you learn something in the first few minutes of what you're doing, and 3 hours later, you've completely forgotten that bit, right? You can remember the last 3 things you saw, but you can't remember that. And so you wind up just, being really good at the last bits that you saw, but completely terrible at the original bits, yeah? So one of the ideas we had in this vein was called RANPAC, right? RANPAC is, it's partly just a a gag on the idea of ransack, which will only make sense to a small number of people in the audience. But ranpack is a very simple idea that you should use a pre-trained model to make the learning process as simple as it can be, right? This idea that we're going to start over here from scratch is just silly, right? So I'm going to use the biggest, best pre-trained model I can get, and I'm going to use it to encode the features, and then I'm going to use a really simple learning method to keep learning through this process, right? And if it's really simple, if my learning's, incredibly simple, it can be fast and it can be flexible to the point where I don't have to worry about losing anything, right? So the other way to do it is you could start with a pre-trained model over here, right? I could start with something enormous. I could start with VIT or VGG or whatever it is, right? And I could try to get some new data. I could try to update that enormous model, right? But updating that model is really expensive, and it's slow and it's computationally intensive and all that sort of stuff. But worse than that, you're updating the parameters of effectively a black box, right? You don't know what the impact is of giving that model new data, right? And one of the kind of inevitable impacts is this forgetting problem, right? So you start training this model that's seen all this stuff that you don't have, right? It was trained by somebody else on data you don't have. You update it on the data you've just seen, and it starts to forget stuff that you never knew it knew, right? So, because the learning process and the representation process are confounded in that big model, it makes it very hard to do that continual learning process, yeah? And continual learning should be relatively simple, yeah? I mean, it's a straightforward idea. So this is, the idea of ranpack is actually really simple. So you take that pre-trained network and you just do random projection on the activations that come out of the pre-trained network, right? So you freeze that pre-trained network. You're never going to try to update it because it's already good at what it does, right? Nothing that you're going to give it is going to update it. It's a great feature encoder, yeah? The question is, what are we going to do with the activations? The idea with ranpack is that you just do random projections and you do a bit of normalization and then you do LDA, effectively, right? LDA is just, it's a really simple, nice, fast classifier. In fact, the reality of what happens in ranpack is even a bit simpler than that, but you can think about it as LDA. And it means that, so your data comes in, your neural network turns it into this complicated thing where the information's already there, but random projections will increase the feature dimension, but in some of those dimensions, the information you're interested in will be separated nicely, right? It's kind of sparse coding theory, and one of the wonderful things about random projections. Random projections are also very fast and they're static, right? So then we can apply our classifier, we can do our lifelong learning, right? Our continual learning to this nicely separated data and do whatever you like. What we do actually is just class means, but which is just a version of LDA really, and it works unbelievably well. In fact, it works. It's the state of the art at the moment. So, that assumes. There's a bunch of problems with that. There's an organism called C. elegans, right? C. elegans is a nematode, right? And so a nematode is a microscopic, it's kind of like a worm, right? It's like a microscopic worm. And they're in the soil, they're all over the place. They're C. elegans, it has the smallest brain of any animal, right? And so it's got 300 neurons in that brain, right? Barely counts as a brain at all. It's so tiny. And the way that evolution has decided to encode the information required for that thing to live and survive and procreate is that it's going to learn, right? You would think that if you were designing some kind of avatar that had only 300 neurons, you would think that you would hard code absolutely everything you could into those neurons, right? Because you're struggling to get any kind of survival strategy into that, yeah? But evolution has decided that if you've only got a budget of 300 neurons, that learning is critical, right? Learning's expensive, and evolution has decided to waste some of those neurons on learning, right? So learning is thus critical to doing the kind of things that C. elegans does, 300 neurons, microscopic thing, and none of the big robots that you've seen in the world, none of the things that we've built can do the things that this nematode can do, right? If you put 2 nematodes in a pot of soil and you come back in 2 months' time, there'll be 1 million nematodes in there, right? If you put 2 robots in a field or a car park or a shopping centre and you come back in 2 months' time, there'll be no robots, right? There won't even be 3 robots or 4 robots, right? There'll be 0 robots. So there'll be 2 piles of junk that look like robots if they didn't get stolen by somebody and taken somewhere and taken apart, right? This thing with 300 neurons is solving a much harder problem than we're solving, right? Most of the problems that we solve are virtual, right? They operate, all of these things that we design really, by and large, the successful ones, operate in online environments, right? Because online environments are very simple. They're constructed by humans to be simple. We give the agents whatever they need to survive. Out in the real world, doing the kinds of things we've just been seeing, right? Robotics and anything that deals with interaction with the real world. Autonomous driving, right? It's one of the worst. You can't just, it's not a symbolic environment, right? It's not an artificial environment. It's not created by humans for the benefit of the things that we put in there. Real environments take completely different strategies and less artifice, right? Okay, so this is one of the latest things we've been doing, which is we call premonition, right? Again, in the theme of trying to move from an artificial version, so an artificial version of the way we frame problems for machine learning, right? This idea that all of the data is going to be given to us, all of the classes are going to be known beforehand, right? Part of that stuff that Simon was talking about before, about the difference between the normal distribution and the uniform distribution, is this idea that all of the classes that we're going to need to recognize, or everything we're going to need to deal with, is predefined, predefinable, fixed, and is going to be enumerated for us. The real world, unfortunately, doesn't work like that, right? The real world is much more complex, but we can make a step towards satisfying those crazy constraints that we have using this idea of premonition. Premonition is just the idea that we can use a large language model and a generative image model to drive the behavior of these algorithms as hard as we can from the very beginning, right? Instead of having to wait until we get over there for it to work, we're trying to figure out how we can get it to work from here, right? So the idea is really very simple, right? If nobody ever gives you a machine learning problem without telling you what it is, right? So we just put the description of what the problem is into the LLM and we ask it what to expect, right? Humans know what to expect. Why shouldn't the algorithm know what to expect? So the top bit there is just, if we're asking it to be a bird classifier, and then we just ask the LLM what kinds of birds there are, right? Really simple idea. The system then, GPT will then tell you all of the most common kinds of birds, right? You can then go back and ask the system to come up with a prompt for stable diffusion that will generate images of those birds, right? And then you can feed those into the model so that it comes prepared for the obvious things it's going to see in that, in its progression. And I know that all the continual learning people in the room are saying, but that's cheating, right? Because, continual learning is supposed to be this big, abstract, cold start, nice, beautiful, theoretical problem that we've been studying for all these years, right? How can we get the best possible, the most information out of this tiny number of incremental bits of data we're getting? Well, it's rubbish, right? Like that's a way to generate bold numbers in CVPR papers, right? The real world means you need to solve the problem right now. And if you're going to solve the problem right now, then you should go in prepared. You should use everything you've got, including these two generative models that will generate the information you need to go prepared, right? So yes, we're cheating. In our defense, in this kind of cheating process, the truth is that if you run this process, it doesn't work, right? It looks very nice. It's very simple to understand, right? You ask GPT what we should expect a bird classifier to have to see. It tells you the birds. We will ask it to construct a description of each of those birds that you can then feed into stable diffusion, and you make a bunch of images for each bird species, and then you put that into your model, and you update your model so it knows what to expect, right? It doesn't work, of course, because the domain gap between the stable diffusion images and the real world is so big that the classifier just focuses on the domain gap, right? And there's been a bit of, we had a bit of a talk about domain gap already, right? But domain gap just means that that the images you get in reality aren't very close to the images that you've trained on, right? So the normal one was, COVID was a cracker, right? So, there was no end of applications that were working very well online right up until COVID hit, and everything changed and all those models broke, right? Because they weren't trained on COVID data, and everybody's behavior changed during COVID, and so, the models couldn't adapt, and they had to be scrapped, right? And when you scrap those models, then you've got to replace them with something. You've got to retrain. But you haven't got any COVID data to retrain them on, right? So, and what happens, the difference between the pre-COVID data and the post-COVID data is a domain gap, right? It means that you've trained on something and you've applied it to something that's quite different. So, but in the vein of the thing we were just talking about, right? In the vein of Rampack, you can use those generated images just to fine-tune your pre-trained model, right? So by and large, if you only remember one thing about all of this stuff, right? It's that training on synthetic images, right? Training on generated images doesn't work, right? You can't just train a classifier on synthetic images because the classifier focuses on the domain gap and the results don't generalize, right? What you can do with synthetic images is transfer learning, right? So you can update a working model using synthetic images. And we were just talking about the fact that we've got a working model, right? We started with a pre-trained model that works very well. So as long as you use those images to fine-tune a model that was already working, then the whole process works, right? There's a couple of papers out there about it. And there's 20 papers out there saying that you can't train a model on synthetic images. But there's a few recently that are pointing out that you can actually fine-tune and it does actually work, right? So, if you go into a driverless car problem, you've got a fair idea about what you're going to see, right? Simon was just talking about seeing kids walking in the road. There's no reason why your driverless car should go into that problem not knowing what to expect. Right? This is tackling that distribution problem that we can give the model information about elephants and ostriches and all of the rare events that it might see without actually having to go and capture every bit of possible training data that it's ever going to see. So this is a synthetic image. One of the fantastic images generated by Midjourney, and it, although the generation models are fantastic, nobody's going to mistake that for a real image, right? There's this incredible, variety of things that you can generate. Anything that you can imagine, you can get out of it. But they all look synthetic. And, as such, bridging the domain gap is a problem we're still facing, right? And it's not going to get any better anytime soon, right? Generative models are getting better all the time, and particularly the image generation models are getting better all the time. But every time they get better, there's still a difference between them and real images, right? And it's always going to be there as far as I'm concerned. But transfer learning, instead of just cold start learning, allows you to bridge that gap, right? All right. So in terms of big takeaway kind of messages, right? The number one thing is that as a discipline, we've framed a lot of these problems artificially, right? And we're not solving the problems that actually matter in terms of applied ML. And you see it all over the place. But one of the main ways you see it is when you get new graduates into an applied research group, is that you've got to train them, you've got to convince them not to just slot the problem into one of the 100 kind of tool sets they've already got, which leads you to bold numbers in the right places, right? The reason that we wound up in that position is really because it's easy to do bold numbers, right? As an academic discipline, it's very easy to train on fixed data sets and assume that the data arrives from on high by magic, right? But the reality, if we're going to make the transition, the reality is that we've got to grasp the fact that real data is horrible and learn to love the details, right? Learn to love the sheer messiness, variety, and dynamism of real data. Right. Thank you.
Thank you very much, Professor Anton Hengel, for your sharing.